Okay, so let's briefly recap what we did last time. So what we've constructed are objects called forms, okay, and or differential forms, and these are tensors of type 0R, okay, which means that they're all lower index type tensors. And the other interesting thing about them is that they're fully anti-symmetric. Okay, so we defined this anti-symmetrization operation last time. And these tensors that we constructed are a subclass of 0R type tensors, which are fully anti-symmetric 0R tensors. Okay, and yeah, so the definition was a differential form of order R or an R form is defined as a totally anti-symmetric tensor of type 0R. Okay, so these are not new objects. These are a subclass of the objects that we are already familiar with, that is 0R tensors. But as we'll see, they have some interesting properties, okay? And they define interesting spaces in themselves, interesting vector spaces in themselves. And more importantly, okay, these differential forms turn out to be the correct objects to integrate on manifolds. Okay, you can't define integration of general objects, but you can define integration of differential forms. So that's basically what we're going to try to build up to. Okay, so another thing we did was to look at an operation between different differential forms. So we talked about the space of differential forms. So the anti-symmetrizer takes you from a tensors of type 0R to these differential forms, which are fully anti-symmetric tensors, which are smooth R forms on M. Okay, so this is the space of R forms. Okay. Then we defined a wedge product, or what is called an exterior product, as a wedge product between two differential forms. So if I have a differential form of type R1 and another of type R2, the wedge product takes me to a differential form of type R1 plus R2, okay, where we define this wedge product as some kind of anti-symmetrization of the normal tensor product with some factors to account for number of permutations. So this is a convention for normalization. Okay. All right, then we saw that, for example, if you have a basis of dual vectors, okay, you can use this to create a basis of using wedge products. You can use this to create a basis of any forms. Okay, so like, for example, two forms, dx mu1 wedge dx mu2 gives a basis of two forms. Okay, and we saw some properties of this wedge product. It's associative, there's linearity, total antisymmetry, and so on. Okay, and then we tried to find a basis for these, and we argued that in n dimensions, the space of R forms is a vector space of dimension NCR. Okay, which in particular means that R forms and n minus R forms are dual to each other or isomorphic to each other. Okay, those vector spaces are isomorphic. Okay, and a general R form, we saw that it can be expanded like this using this basis of R forms, okay, which is expressed using the wedge product. Okay, then we did some counting, okay, of the number of R forms. So for 0 forms, there's NC0 and so on, okay. And basically beyond n, okay, so the dimension of the manifold is n. The maximum size of n forms that of R forms that you can have is omega n, okay, where R is equal to n. And there's only one basis vector associated with this R form, or this n form, okay. Because this is the fully anti-symmetric dx1 wedge dx2 dot 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 wedge dxn. There's only a unique choice of these indices, okay, which gives you this n form. Okay, we looked at some more properties of the wedge product, and yeah, okay. So now today we're going to start here. Okay, so we're going to continue our discussion on forms. Okay, and we're going to define some more operations on forms. So this is probably one of the most important operations that we'll talk about, which is the exterior derivative. So we'll first define this exterior derivative in a coordinate dependent way, and later we'll show that our definition is actually independent of any coordinate system that we use. Okay, so this is a different derivative. So we've learned about two different derivatives now. Okay, we've learned about the derivative delta. This is associated with a connection, on a manifold. Okay, and this is the affine connection, and it satisfies certain properties. It requires additional structure on the manifold to define this derivative. Another derivative we looked at was a Lie derivative, which requires a vector field. Okay, you need to specify a vector field to take a derivative. Okay, so it's sort of comparing like tensors as I flow along this vector field x. It's the comparison of tensors at two nearby points. Okay, when I flow along the vector field x, that gives me the Lie derivative. So both of these require you to specify something. Okay, the connection requires you to specify a connection on the manifold to compare tensors, because I have to tell you how to parallelly transport the tensor. Or the Lie derivative requires that you tell me what the vector field x is so that I tell you in which direction to compare the tensors. Okay, but what we'll see is something special about differential forms is that you can define a derivative that doesn't really require you to specify any additional structure on the manifold. Okay, it doesn't require you to specify a vector field along which you're taking a derivative, and it doesn't require the existence of a connection to tell you about this derivative. Okay. So this is yet another kind of derivative, but this derivative is not a derivative that you can take of any arbitrary tensor. It's a derivative associated with differential forms. Okay, and this derivative, which we denote as dr, takes us from R forms to R plus 1 forms. Okay, whereas if you recall the, for example, the L, okay, or Lx. Okay, what it did was it took us from tensors of type QR. It took us again to tensors of type QR. Okay. Similarly, del along, if we took the fine connection along a particular direction, it took us again from tensors of type QR to tensors of type QR. Okay. In this case, this derivative takes you to tensors, or it increases the rank of the tensor by 1. Okay, or the rank of the differential form by 1. Okay, so again, we'll define it in a coordinate dependent way. So let's start with some particular R form, okay, which we'll write without loss of generality. Omega is equal to 1 by R factorial, omega mu1 through mu r, dx mu1, wedge dot dot dot, wedge dx mu r. Okay. And this is our R form. And now we'll define the action of this derivative, dr omega is equal to 1 by R factorial times partial nu acting on omega mu1 through mu r, dx nu wedge dx mu1 wedge dot 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 wedge dx mu r. Okay. Now, the first thing is when you look at this expression, okay, you see that you've introduced a derivative here. This is like a regular derivative. Okay, but it's a coordinate dependent derivative, right? So it depends on what coordinate system you're using. Partial nu is partial of x nu, where x nu are those coordinates. So it's not obvious that at the moment that this definition is coordinate independent. Okay, but we'll see in a few moments that it really is coordinate independent. The second thing is that if you look at this quantity here, okay, this is fully antisymmetric. We've introduced a dx nu and we've summed over nu, okay, this index nu. And now we fully antisymmetrized by taking the wedge product of dx nu with all of this, we fully antisymmetrized automatically. And therefore, even if this coefficient was not antisymmetric, it now becomes antisymmetric. You're only picking up the antisymmetric piece of this entire coefficient. Okay, so it's automatically antisymmetrized by this definition. And therefore, this is automatically an element of omega r plus 1. Yeah. Okay, so it certainly appears to be a map from here to here. What is not obvious is that this map is coordinate independent. Okay. Okay. Now, from now on, we will denote this d with the subscript r. We'll denote it as just d. Okay. And where the r is understood from the context, depending on what is the rank of the form that you're differentiating. Okay, we will automatically understand what is meant by the r associated with that. Okay, this can be a little confusing, but it's the standard convention. Okay, is to drop the subscript r. Okay, when needed, we'll reintroduce the subscript r just to remind ourselves what we're differentiating. Okay, so let's do some examples, okay, with this definition. So let's take R forms in 3D space. Okay, so this is without taking any kind of exterior derivative. Let's consider R forms. Okay, so if we consider R forms, so if we take 0 forms, there's only, so in 3D space, so we're taking n is equal to 1. Remember the number of R forms is NCR, okay? So if we take 0 forms, there are 3C0, and those are basically just functions, okay? So omega is equal to f of x, y, z, okay? This is a 0, 0 type tensor. It's just a smooth function on the manifold. Then what we can do is we can take, so I'm just assuming R3, for example, right, with coordinates x, y, z. Then what we can do is we can take, so this is the manifold that we're assuming. Then what we can do is we can take, instead, we can take n is equal to 2, sorry, n is equal to 3, r is equal to 2, sorry, r is equal to 1. So that gives us 3 1 forms, okay, 3C1, 1 forms. And these 1 forms are either, the basis of 1 forms is either dx, dy, or dz, okay, these are 1 forms. And we can have any arbitrary coefficients for them, omega x of xyz, omega y of xyz, omega z of xyz. And so the linear combination of these gives me my 1 forms. Similarly, we can get our 2 forms. Okay, our 2 forms, again, there are 3C2, which is 3 2 forms. So the basis of 2 forms is dx wedge dy, dy wedge dz, and dz wedge dx. Okay, you don't need to write dy wedge dx because dy wedge dx is the same as dx wedge dy up to a minus sign. Okay, so the basis of 2 forms, there are only 3 of them, okay, in 3 dimensions. And the coefficients are omega xy, omega yz, omega zx, and these coefficients are fully antisymmetric. That is, omega xy is equal to minus omega yx. If there was a symmetric part, that would automatically, get set to 0 once you multiply it by this antisymmetric piece dx wedge dy. Okay. And again, these are this omega xy, omega yz, omega zx. These are also functions of xyz. They can vary depending on where you are on the manifold. And we're assuming that these are all smooth functions. And finally, if we come to our 3 forms, 3C3, so there's only one 3 form, which is omega xyz, which is a function of xyz, dx wedge dy wedge dz. Okay. Now, the claim that we are arguing is that there is an isomorphism, okay, because this is a one-dimensional vector space. This is a one-dimensional vector space. There's only one basis vector. The basis vector here is 1. The basis vector here is dx wedge dy wedge dz. Okay, so therefore there's an isomorphism between these two things, these two vector spaces. Similarly, there's an isomorphism between this vector space omega 1 and the vector space omega 2. Okay, when I say vector space, I mean vector space more generally, in the sense that forms are, of course, 0R tensors, which are fully antisymmetrized, but any tensor is also tensors of rank QR also define a vector space. Okay, in the sense of adding them and so on. Okay. So how do we see this isomorphism? Well, the isomorphism is kind of easy to see because here I just have a single function omega xyz, and here I have a single function fxyz. So we can just do a direct mapping, okay, between fxyz and omega xyz. Here, if we want to see the isomorphism, okay, between this and this, we could define some kind of isomorphism like this, like omega xyz can be mapped to omega yz, okay, and similarly omega y xyz can be mapped to omega xy, and omega z xyz can be mapped to omega zx. Okay, so if we define this Levi-Civita symbol as epsilon mu nu lambda, such that what we mean by this is, remember that permutation symbol. Okay, so if I take a permutation defines a particular permutation, so this operation P defines a particular permutation. So let's say it takes you to 3 to 1. So P1 is then defined as 3, P2 is defined as 2, P3 is defined as 1. So 1 got permuted and became 3. 2 got permuted and became 2. 3 got whatever was supposed to be in 3's place is now 1. Okay, so that's what we mean by these symbols P1, P2, P3. So epsilon of P1, P2, P3 is equal to minus 1 raised to P, where P is the sign of the permutation. Okay, it's so this minus 1 raised to P is the total sign of the permutation. So in this case, this is an odd permutation. So this P is odd. Okay, and minus 1 raised to P would be minus 1. If it's an even permutation, then you would get a plus 1 here. Okay, so this is your usual Levi-Civita symbol. And now what we can do is we can do a mapping. Okay, so if we take those, so what I said about that mapping between omega yz and omega x is basically this mapping. Okay, writing the alpha mu, where I call these alpha mu's, okay, alpha x, alpha y, alpha z, okay, is related to the omega nu lambda, okay, by this kind of mapping. Okay, so its vectors are mapped to two forms. Okay, two forms are basically mapped to vectors. And you understand right away what this kind of mapping is. Okay, it's some kind of I mean, you can think of it as some kind of axial vector. Okay, so it still behaves like a vector. Okay. um, all right. So now that we've looked at these zero forms, one forms, two forms, and three forms. Sorry, yeah, zero forms, one forms, two forms, and three forms. Now let's look at the action of the exterior derivative, d. Okay, so let's take d omega 0, where omega 0 is the zero form. Okay, it's just fxyz. So what this d omega 0 does is it converts a zero form to a one form. So first of all, the fact that it's a one form means that we'll get dx, we'll get dy, we'll get dz, because this is the basis of one forms. And then the coefficients will be partial f partial x, partial f partial y, partial f partial z. Okay, so if you look at the coefficients, this is very reminiscent of how you take the gradient. Okay, this is how you take the gradient of a function. This will be the gradient partial f partial x, partial f partial y, partial f partial z. Okay, just that these things are multiplied by dual basis vectors, or actually basis of vectors of one forms. Similarly, you take d omega 1. Okay, so again, let me just remind you the definition of d omega. We'll go back here. Okay, it's 1 over r factorial partial nu omega mu1 dot 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 mu r dx nu wedge dx mu1 dot wedge dot 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 dx mu r. Okay, so I introduce a derivative, okay, and then I put in dx nu over here. So if I start with omega 1, okay, omega 1 was these one forms here, this one form here. So now what we do is each one we differentiate. Okay, so for example, we differentiate omega x. So let's write that. Okay, so we differentiate omega x. So let's say with respect to x, y, z. So we'll do this omega x dx wedge dx plus we differentiate with respect to y. This is the sum, right? Omega y dx, sorry, dy wedge dx plus partial z omega, sorry, again, this is omega x. Partial z omega x dz wedge dx. Okay, and similarly, you have to differentiate these other terms, okay, which I'll do in a moment. But when you look at this, okay, what you see is dx wedge dx is 0, okay, because it's the wedge product is already antisymmetric, okay, and dx wedge dx when I antisymmetrize is equal to minus of dx wedge dx when I exchange these two. Therefore, dx wedge dx is 0. So this vanishes, okay, and so I pick up two terms like this, one term like this and one term like this. Now, this is the term that I get from differentiating this term, but I will also get a term from differentiating this, which will be of the form partial x omega y dx wedge dy. Okay, so now what I can do is I can club this term with this term because dy wedge dx is really the same as dx wedge dy. Okay, except that I will get a minus sign here when I exchange the order. If I exchange the order, I will get a minus partial y omega x. So the net effect is that I get a term like partial x omega y minus partial y omega x. Okay, dx wedge dy. So if we see what we have here, okay, d omega 1 will be partial omega y partial x minus partial omega x partial y dx wedge dy. And similarly, I'll have other terms for dy wedge dz and dz wedge dx, partial omega z y minus partial omega y partial z, partial omega x partial z minus partial omega z partial x. So if this was the gradient, this term should be very reminiscent of how you take the curl of a vector, right? So if I have a vector omega x hat plus omega y hat plus omega z hat, This is very similar to taking the curl of that vector field. Okay, these are the coefficients of the curl. Okay, and similarly, if we take d omega 2, okay, what we'll get is, so now we're differentiating a 2 form, so we'll get a 3 form, and there's a unique basis element for a 3 form, which is dx wedge dy wedge dz. So we'll get partial omega yz partial x plus partial omega zx partial y plus partial omega xy partial z, okay, times dx wedge dy wedge dz. Okay, so this is very similar to the divergence. Okay, so if you remember the isomorphism that we said, omega yz is very similar to some alpha x, omega zx is similar to some alpha y, and omega xy is similar to some alpha z. Okay, so this is like the divergence del dot alpha. And finally, d omega 3 is just 0. Okay, that is, if you differentiate a 3 form, you'll get 0. Why is that?
So 3C4 is 0.
Yeah, that's one way to think about it. Or if you look at the definition, your 3 form is already this, right? And if I differentiate it, I'm doing a dx nu wedge this, okay, some partial nu of omega 3. And I have to sum over all these new indices. Now, it doesn't matter what I put here, whether dx, dy, dz, okay, in 3 dimensions, if I repeat the index, okay, anywhere inside this wedge product, then this is automatically 0 because this has to be anti-symmetric in every 2 indices. Okay, so d omega 3 is 0, or yeah, another way of saying it is 3c4 is 0. In fact, you define this to be 0. Okay, so here's a homework exercise for you. Okay, so prove that if psi is a q form and omega is some r form, then d of psi wedge omega. So now if I take the exterior derivative, sorry, of this wedge product, psi wedge omega, then that is equal to taking the exterior derivative of psi wedging with omega, and then taking psi wedge d omega, except that there's going to be a factor of -1 raised to q, okay, over here. Intuitively, the way you think about it is the d acts on psi, okay, through the derivative, but when the d acts on omega, I have to think about it as moving q places over. I have to move q places past this psi, okay, and then act on the omega. So when I move q places past this psi, I get a -1 raised to q. Okay, roughly speaking, you can think of the d as sort of for every every odd number of indices that it crosses, right? Then you pick up a minus sign. Oh, sorry, for every index it crosses, it picks up a minus sign. Okay. Okay, so just homework to prove this. Okay, it's not very hard to do this. Okay. Okay, so now this definition that I showed you again looked a bit weird, right? It looked like it depended on the coordinate system that you use, but what we'll do is we'll show that there is a coordinate-free expression for this exterior derivative. Okay, so let's start by doing this. Let's take a 1 form, which is omega is equal to omega mu dx mu, and we'll take 2 vector fields. So we'll take this vector field x and this vector field y. Okay, and we'll argue that d omega is actually a 2 form such that d omega of xy, okay, so d omega is a 2 form. It takes in 2 vectors as inputs because it's a 0-2 type tensor. It takes in 2 vectors as inputs. Okay, and it's fully anti-symmetric, which means that this is equal to d omega yx with a minus sign. Okay, and what we'll argue is that this d omega xy or minus d omega yx, this is equal to x acting on omega y. Omega acting on y is a 1 form acting on a vector. Okay, so it's a product of a dual vector and a vector. This is a function. Okay, and x acting on that is a vector acting on that function, right? Or it's differentiating that function. So this is also sorry. Yeah. So this is a function of the manifold minus y acting on omega x. This is also a function on the manifold. minus omega of the Lie bracket of xy. Okay, so this Lie bracket of xy is also a vector field. Again, when I take a dual vector acting on a vector, that's like the dot product or the inner product of these two. Okay, which is a metric independent notion. Okay, because we have a dual vector and a vector. And so this quantity on the right side, you can clearly see that this doesn't require any definition of coordinates, right? All of these operations, that is products of vectors and dual vectors, or a vector acting on a function, right? That vector acting on a function is defined through curves and taking gradients along those curves. All of these notions are coordinate independent. So at least in this case, what we're arguing is that for a general xy, okay, we're showing how if I supply these two x and y's as inputs to d omega, how I can think of that operation, okay, as as a different kind of operation involving x acting on omega acting on y, minus y acting on omega acting on x, minus omega acting on the Lie bracket of xy, where all of these, okay, are coordinate independent operations. So therefore, d omega itself is a coordinate independent operation, okay, because this is true for any x and y. So if we show this, basically we've argued then that basically d omega is a coordinate independent operation, even though the way we defined it seemed to indicate that it was not obvious that it's coordinate independent. Okay, so this expression will be quite useful. So in a particular coordinate patch, okay, what you can do, for example, so let's prove this identity. Okay, we'll prove that this is true. Okay, so we'll work in a particular coordinate patch. So d omega acting on xy by definition. So we'll write down what d omega is. So omega is like omega mu dx mu, and then if we d omega is partial nu, and we introduce a dx nu wedge dx mu. Okay, and there's a one factorial because it's a one form. Okay, that's it. And this whole thing acts on xy. And our xy are expanded like this. They're expanded in terms of basis vectors as x mu coefficients of partial x mu and y mu coefficients of partial x mu. Okay, so so now this is going to give me, so this dx nu wedge dx mu, this is dx nu, we worked this out last time, tensor product dx mu minus dx mu tensor product dx nu. Okay, so when this acts on xy, okay, this is going to give me the x nu coefficient. This is going to give me the y mu coefficient. This is going to give me the x mu coefficient, and this is going to give me the y nu coefficient. So what I get is partial nu omega mu x nu y mu minus x mu y mu. Okay, so this is the left-hand side of this equation. Okay, now we need to argue that the right-hand side of this equation also gives us exactly the same expression. Okay, and if it's true in any coordinate patch, then basically the right-hand side is anyway a coordinate independent definition. So that would mean that this would be true in a coordinate independent way. So for a general R form, okay, so I leave this as homework, okay, to show this, but basically you can also expand the right-hand side and you can show that you will get exactly the same expression. Okay, it's not very hard to do. Okay. Now what you can do is you can also argue that for a general R form, okay, what we showed is for one forms, okay, we showed that there's a coordinate independent definition of what we mean by d omega. Okay, you can generalize this to R forms. Okay, so d omega of some R form, it takes in, this should be an R plus one form, which means it takes in R plus one vectors as inputs. And you can show that what this is equal to is that this is equal to the dual vector, sorry, or this R form acting on x1 dot 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 to xr plus 1, where I omit one of the xi's. Okay, and then so this is now going to give me, it's an R plus 1 form acting on R vectors. So that is going to give me just a one form. Okay, at the end of it, it's just going to be a one form. And this one form is a dual vector. So I take this inner product of this dual vector with xi. Okay, but there's going to be a coefficient minus 1 raised to I plus 1. And so this is summed over all possible choices for this xi. Okay, and also there's a minus 1 raised to I plus j omega acting on the Lie bracket of xi xj, where now I omit xi and xj here. Okay, and and I have x1 dot 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 till xr plus 1, okay, where I omitted the xi xj. So this is an R form, okay, and we have 1 plus r plus 1 minus 2, okay, of vectors that this is acting on. Okay, so therefore this is r plus, this is acting on r vectors. Okay, so when it acts on r vectors, what we get back is a scalar function. So this is a scalar function, this is a scalar function, this is a scalar function on the manifold. Okay, so, and this is a coordinate free expression, right? Because the action of a dual vector on vectors or a vector on a dual vector, all of these operations are coordinate independent, or this Lie bracket is a coordinate independent notion. Okay, so since this has a coordinate free expression, okay, it shows that basically that the definition that we gave, we could have taken this as the alternative definition, okay, of what we mean by this exterior derivative. Okay, but that notation, even though it's coordinate dependent, at least it makes it more clear what you're doing. Okay. Um, okay, any questions here?
Sir, in this expression, in the first term, like if we omit one vector, then there are r vectors.
Oh, sorry. Yes, there are R vectors. Sorry, I made a mistake. You're right. There are R vectors, and this is not a one form. It's a zero form. That is, it's a function, and this xi acts on that function. Okay, so that's similar to this expression that we had here, x acting on omega y. Okay, um, that's what we had here, right? We omitted one of these xy. So we omitted x and then we put y here and we acted omega on y and then we act x on that. Okay, so sorry, it was not a product. It's xi acting on this. And then this comes with a plus sign, but when you omit the y, okay, and you act omega on x and then you act with y, you get a minus sign. Okay, so that's basically both those first two terms are encompassed in this term. And this third term over here, omega acting on xy, okay, that is encompassed over here because basically you've omitted everything because you only had two arguments. So I dropped two arguments and I had omega acting on xi xj. The only thing is I have to put a minus sign. Well, in this case, there would be a minus sign, yeah. Okay, I plus j is 1 plus 2, which is 3. Yeah, thanks for the question.
Yeah, sir, one thing, but the left hand side is like d omega is 0 r plus 1 form, and it takes in r plus 1 vectors. So left hand side has a function.
Yeah, left hand side is a function, but the right hand side is also a function. Right?
Oh,
This is a vector acting on a function is also a function, right?
also a function. Yeah.
Okay, now there's another way to see the coordinate independence of this exterior derivative, but this is using assuming that you have a connection on the manifold. Okay, so if you have a connection on the manifold d omega, okay, you can show in appendix B of Wald, okay, it shows that you can write this this derivative, okay, using something like this. So del, okay, where this is now an affine connection rather than the regular derivative. Okay, del nu of omega mu1 through mu r, where these are anti-symmetrized, okay, where you're anti-symmetrizing over all these indices, dx mu1 wedge dot 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 wedge dx mu r. Okay, and you multiply by this extra factor of r plus 1. I think you want dx nu wedge all of this. Oh, sorry, this isn't okay. Here, these are just tensor products, okay? These are just tensor products. And what I told you earlier, right, is so this by definition, this anti-symmetrization has a 1 by r factorial in it. Okay, it has a 1 by r factorial here. And what I told you is you can either anti-symmetrize over these indices or you can take a wedge product of these objects. Okay, so instead you take a wedge product of these objects. And now what happens to this derivative here, okay, this affine connection, is that we've seen that the affine connection acting on a 0R tensor basically will give you a series of terms which involves this Christoffel symbol, gamma, lambda, nu, mu, omega, mu1, dot, 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 lambda, dot, 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 mu r, dx nu, wedge, dx mu1, wedge, dx mu r. Now this Christoffel symbol, all the indices of the Christoffel symbol and these indices, all of these, except for the lambda, except for the lambda, okay, all of these indices are anti-symmetrized over. In particular, what it means is that the Christoffel symbol indices are anti-symmetrized over. And the Christoffel symbol is already symmetric, okay, if it's a torsion-free connection. And so therefore, this is equal to 0, okay, which means that this expression, when I use a symmetric connection, not necessarily a metric connection, any symmetric connection, okay, this is exactly the same as the expression that we had written down earlier, okay, because the Christoffel symbol coefficients all drop out. Okay, so again, what this means is that no matter what choice of connection you use, torsion-free connection you use, okay, you always get this expression. Okay, the one we had defined for d omega. Okay, so basically d omega is some kind of anti-symmetrized derivative operation, which is actually independent of the exact choice of the connection that you use. Okay, which is why it looks strange that we use this particular derivative, which is a coordinate dependent derivative, but you really see that the coordinate dependence kind of is artificial in the sense that you could have used any connection and d omega would have, you could have used any connection to define this derivative. So instead of using this, you could have used any general connection to define the derivative, and you would have still got effectively the same result, okay, for d omega. Okay. Okay, now that, so we're going to continue a little more with this discussion with this exterior derivative, okay? So here's a very important formula now about this exterior derivative, okay? So the formula is that it's very simple, d square is equal to 0. In other words, what we mean is dr is a derivative which acts on an r form, okay? So omega is an r form. So let me write small omega. Okay, and now this is an r plus 1 form. And so when I act with the derivative, I have to act with an r plus 1 derivative. So when I say d square, what I really mean is dr followed by dr plus 1. Okay, this operation always results in 0. Okay, it gives me 0 as a function on the manifold. Every point of the manifold will give me 0. So what is the proof of this? So let's take omega, okay, which we'll use the coordinate dependent definition, okay, which looks like this. D square omega will be equal to 1 over r factorial. So now basically all I'm doing is I'm introducing two derivatives, partial square, partial x lambda, partial x nu, and I introduce two wedge products, partial x lambda, partial wedge x nu, wedge dx mu1 dot 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 wedge dx mu r. Okay. Now it's obvious why this is 0. Okay, this is symmetric in lambda and nu. If I exchange lambda and nu, this is symmetric, but this is anti-symmetrized in lambda and nu. Okay, so so therefore this is just equal to 0. Okay, so d square omega is just 0. So I'll give you a familiar example of where you have actually secretly already seen something like this. Okay, and this is rather surprising if you've not seen it before, but it'll become obvious why. So define A as A mu dx mu. Okay, so where A mu is like some kind of electromagnetic 4-vector potential. Okay, so it's the scalar part and then the vector part of the potential. Okay, A mu dx mu. Okay, so this is a one form. So you can think of the electromagnetic potential as a one form field, okay, defined over a manifold. And F is equal to dA is now a two form, okay, which is the field strength tensor. So F is equal to 1 over 2 factorial F mu nu dx mu wedge dx nu. This is just a definition of what we mean by F mu nu. And dA, okay, is equal to partial mu A nu dx mu wedge dx nu. This is just a definition of what we mean by the exterior derivative acting on a mu dx mu. Okay. And so if we're saying f is equal to dA, that gives us a relationship between these f mu nus and these partial mu a nus, these coefficients, partial mu a nu. Okay. And that relationship is basically saying that we equate the coefficients of dx mu wedge dx nu. And so what we're saying is f mu nu is equal to partial mu a nu minus partial mu a mu. Okay. Why is that? Well, if you look at this coefficient is not antisymmetric, but this coefficient is antisymmetric. Okay. And so if I want to write this as an antisymmetric coefficient, I would write it as partial mu a nu minus partial mu a mu. Okay, 1 over 2 factorial dx mu wedge dx nu. Now this is antisymmetrized. Okay. Why was I justified in doing this? Well, because I can always swap the mu nu indices. So I can relabel the mu and nu indices here as, so in the second term, I can write it as partial mu a nu minus, I can swap the mu nu indices in the summation. I can relabel them as mu nu. And then, but now it would multiply dx nu wedge dx mu. Okay, whereas this term multiplies dx mu wedge dx nu. And now I exchange the order of dx mu and wedge dx nu here, which would give me a plus sign. Okay, and so this would be dx mu wedge dx nu. Okay, and then that would cancel with this factor of, so I get a factor of 2, which would cancel with this factor of 2 in the denominator. So that's how f mu nu is equal to partial mu a nu minus partial mu a mu. Okay, so that's rather wonderful, right? That you have basically an expression for the field strength tensor, which is a 2 form, which is expressed as the exterior derivative of a 1 form. So this f mu nu is, as you're already familiar, maybe from special relativity or electromagnetism, is the 2 form field strength tensor, which can be expressed as 0 minus ex minus ey minus ez, ex ey ez, 0 bz minus by bx. Okay, so this kind of antisymmetric tensor. These are the components of f mu nu. So this is the 0, 0 component, 0, 1, 0, 2, 0, 3. Okay. Where the electric field is, so if you use these equations, it tells you that the electric field, which is something like f0i, right? I should be careful and always use lower indices actually to define this. Okay, is equal to some derivatives, okay, of a0 partial I a0 minus partial ai x0. Okay, something like that. Okay, so this is what we have for f0i. Is equal to is equal to e. Sorry, and this is minus f0i. Okay, so that's why f0i is equal to partial I a0 plus partial. Maybe I'm getting the signs wrong. Yeah, sorry, you have to be very little careful here. There's a minus sign here as well. Okay. Anyway, I'm not being very careful about this. Okay. So you'll get a plus AI here. So what you get is something like this. Okay, sorry, I should be more careful about the signs. Okay, and what shows up here. In any case, so this is roughly the idea. Okay, that the one form is A can be written in terms of the electromagnetic vector potential as A mu, and F can be written as dA. Okay, so in a very compact notation, F is equal to dA. Okay, where what you mean by F is, you know, these coefficients F mu nu times dx mu wedge dx mu. And now let's consider dF. Okay, now dF is equal to d square A. Okay, because it's exterior derivative acting on dA, and that should be 0 by what we've just argued. But this is basically what is called the Bianchi identity. Okay, in other words, what we're arguing is that dF is 0, which means dF is equal to 1 over 2 factorial partial mu f nu rho dx mu wedge dx nu wedge dx rho. This is just a definition, okay, of the exterior derivative acting on a 2 form. And what that tells you is the fact that this is 0, okay, tells you that partial mu f nu rho. Okay, so now I can expand this in terms of tensor products. Okay, and I can take the coefficient of a particular term in that tensor product, and what I would get is this. partial mu f nu rho plus partial nu f rho mu plus partial rho f mu nu is equal to 0. Okay, or if I multiply this by epsilon mu nu rho sigma, okay, this is basically the statement that partial mu f twiddle, okay, is equal to 0. F twiddle mu nu is equal to 0. Sorry, mu sigma is equal to 0. Okay, but basically this equation, if you express it in terms of B and E fields, is two of Maxwell's equations. It's the equation del dot B is 0, and it's the equation partial B partial T is minus del cross E. Okay, this is the Bianchi identity. Okay, how do you get Maxwell's equations for free? Well, you actually get them from the fact that B can be written is divergenceless means that B can be written as the curl of some field. So already by the fact that you're defining F to be some dA, okay, that already guarantees that you're going to get something like this to be true. Or in other words, dF will be 0. Okay, which is basically two of Maxwell's equations. So two of Maxwell's equations are written in a very compact form. You're just saying dF is 0. Okay, and this is really coming from the fact that d square is equal to 0. Okay, so the fact that F is equal to dA implies dF is 0. Okay, so the fact that you could write F in terms of a exterior derivative of the one form vector potential means that you get Maxwell's equation, two of Maxwell's equations for free. The divergence of the magnetic field is 0, and the curl of the electric field is minus partial B partial T. Okay, so that's rather wonderful. The other two Maxwell equations, in case you're wondering, I'm not sure we'll have time to discuss it, so I'll just tell you right now, is you have to define something called a star operation. Okay, the star operation requires you to define a metric on the manifold. So you can't define this without a metric. Okay, so this is called the Hodge star operation. But the other two equations require a metric on the manifold. And if I have a one form current, J, which is J mu dx mu, okay, then the other two Maxwell's equations can be written. So the star F is like somehow taking like an epsilon on F. Okay, so d star F will be equal to star J. Okay, so basically you can write Maxwell's equations very compactly. This is basically all of Maxwell's equations just written in the most compact way you can imagine. D star F is star J, dF is equal to 0. Okay, this has the other equations. Del dot E is equal to rho, and del cross B is equal to partial E partial T plus J. Okay, all of that is encompassed in these two equations, and the other two equations are here. Del dot B is 0, and del cross E is, so the source free equations are here. Okay. And that's it. So you can get Maxwell's equations. This is probably the most elegant way of writing Maxwell's equations, okay, using the language of differential forms. Okay, the second one is an automatic property of the fact that F is equal to dA. F can be written as an exterior derivative. Okay, and it doesn't require any definition of a metric, okay, to interpret this. To interpret this requires a definition of a metric. Okay, I'm not going to go into the details of this Hodge star. Okay, maybe that's for a later discussion. Any questions here?
Sir, I have one question. Like, sir, when you defined that A as one form, so A that was A mu dx mu. But like if we want to express a Maxwell's equation in terms of vectors, then that A vector is if I think of that as the three components of a four vector, then unless I have a metric, I cannot actually go from this to that, I guess. And if I want to write in terms of vectors.
Yeah, you think of it as dual vectors, okay, and you work with that. If I want to get the vector, then I need a metric. Yes.
Yeah. So maybe that equation that you had that had three vector A. So that's why that minus sign was. Yeah. That this one minus gradient of phi minus del three vector A del x0.
This one.
Yes, sir. Yes, sir.
Okay, but what I do is I interpret this as the three components of this object. I mean, it's just a way I choose to write the three components of this object. Okay, obviously this is inspired by the fact that I'm interested in Minkowski spacetime, but I can always expand A0, A1, A2, A3, and just give this a definition where I call this minus A x, where what, right? Because this will ultimately be related to AX in Minkowski spacetime. Does that make sense?
Yes, yes.
Yeah, I mean, so in fact, this property is actually quite the fact that f is equal to dA and df is 0. Okay, these equations will not change in any Minkowski in any spacetime background. Okay, it's the other equations that change when you have a different metric on the manifold.
So sir, like in any arbitrary curved spacetime, this df equal to 0 will hold. So those two equations always be true.
Right. Well, even the other equation will be true, except that the star will mean different things in different backgrounds. The hot star operation means different things in a different background. So this equation is also true in an arbitrary background, except star means different things. It's a metric dependent definition. Okay. Okay, so let's discuss some more properties, okay, of these differential forms. So we've seen before that if we have a map from a manifold M to a manifold N, okay, so this map is F. So it takes a point P to a point F of P. Then we've seen that if you take dual vectors, T, F, P star N, okay, then there's a pullback map that you can use, F star, which defines dual vectors on TP star M. So given a dual vector here, okay, it'll identify for me a dual vector over here. That's a pullback map. And in general, if F is not a diffeomorphism, then you can only define pullbacks. You cannot define the push forward of dual vectors. Okay. And we've also seen that this can be extended not just to dual vectors, but any tensor of type 0R. Okay. So in particular, it applies to R forms as well. Okay, that is, you can pull back R forms. So if I have an R form here, I can pull it back and get an R form on the manifold M when I have this map F between these two manifolds. So if I have an omega belonging to omega Rn, okay, then F from M to N for each point F of P, we can get a pullback. Okay, so F star defines a pullback of a form, R form on N to an R form on M. Okay, that is, if we take the pullback of omega acting on vectors x1 through xr. Okay, so these are vectors at the point here. So these are various vectors x1 through xr. And now I have a dual tensor here, or sorry, an R form here. I pull it back, I get the form F star omega. I act as F star omega on these R vectors. Then the claim is that that should be equal to omega acting on the push forwards, x1, F star x1, F star x2, F star xr. Okay, this is by definition of what we mean by the pullback map and how it's related to the push forward map. You can push forward vectors or pull back dual vectors. Okay, so this is true, and since omega is fully antisymmetric, that is, if I exchange the orders of these x1s and x2s, okay, any odd exchange will give me a minus sign overall. Therefore, it must also be true that F star omega is also odd under the exchange of these x1s through xr's. Okay, so under the exchange of this F star x1 through F star xr, okay, if this is odd, it's also odd on an exchange of x1 through xr. And therefore, this F star omega is obviously a 0R tensor, but it's also a 0R form because it's fully antisymmetric. Okay. Now, just a few more things. So if xi and omega are R forms, okay, on the manifold N, and F is a map from M to N, okay, then what we can do is we can take F star omega, which is, we start with, okay, let me just draw the picture here. This is M, this is N. Okay, this is P, this is F of P. There is some dual, some R, 0R10, some R form here. Okay, this belongs to omega R. I pull it back, I get F star omega, that's here. And now I take the exterior derivative, okay, on this manifold. I take the exterior derivative on M, okay, of the pullback of the R form, okay. That is equal to, okay, you can show that that is equal to the taking the exterior derivative on this manifold. That is, I take d omega, okay, and I pull back d omega. So I take F star of d omega. So if I pull back after taking the derivative, that's the same as first pulling back and then taking the derivative. Okay. And note the thing is that when I first pull back, this is an R form, and then I'm differentiating it to get an R plus 1 form. Here I am differentiating an R form, getting an R plus 1 form, and I'm pulling back not an R form, but I'm pulling back an R plus 1 form. Okay, so these operations mean something different. This is D of an R plus 1 form. This is a pullback of an R form. This is a pullback of an R plus 1 form, and this is differentiation of an R form. Okay, so this is something that you can show this again. I'll leave as a homework exercise. Okay, and F star of psi wedge omega is equal to F star of xi wedge F star of omega. That is, I pull back both of them and take the wedge product. That is the same as pulling back the wedge product. Okay. Okay. Now there's a sequence of maps which are introduced by the exterior derivative. Okay, so this is actually a pretty interesting discussion, although it's not strictly relevant for what we're going to do in GR, but it's relevant for understanding things like magnetic monopoles and many other things. Okay. Okay, so here's the idea. Okay, so you have your various R forms. Okay, so you have omega 0. Okay, this is 0 forms. This is the space of 1 forms and so on. And the derivative basically is an operation that takes you from 0 forms. D0 takes you from 0 forms to 1 forms. D1 takes you from 1 forms to 2 forms. Okay, and so on. So Dn minus 1 takes you from n minus 1 forms to n forms. Okay, if I act further with the derivative, I will get 0. Okay, so you can think of this as a map to basically the set 0. Okay, and similarly, we can define something called an inclusion map 0, which is basically taking us from 0 to the 0 function on the manifold. Okay, which is an element of omega 0 m. Okay, so here, so 0 is an inclusion map, which basically takes me from 0 to the 0 function on the manifold. So f on the manifold at any point on the manifold is just 0. Okay, so now this sequence of maps over here is called a Dirac complex. Okay, and another interesting property of this is that if you look at the sequence of maps, okay, when I take this and I act with D0, okay, on this, I will go here. Okay, so this basically these derivatives are not going to give me all the 1 forms. Okay, so derivatives are one class of 1 forms. So I'll have, for example, suppose I start with so supposing I start with R forms. Okay, so omega is an R form and I take a derivative of it. Okay, this will of course be an R plus 1 form. But this list of R plus 1 forms is not exhaustive. This will not cover the space of all possible R plus 1 forms in general. Okay. However, when I take the maps from R plus 1 forms, okay, let me denote them as psi, R plus 1. When I take the derivatives of these, okay, some of these, as these of course belong to omega R plus 2. Okay, only some of these are 0. Okay, only some of these derivatives are 0. Okay, among those things which have derivatives 0, okay, are these objects. Okay, that is dr omega r. Okay, so this gives me a subset of the r plus 1 forms. And there are furthermore some r plus 1 forms whose derivatives are 0. Okay. Uh, so what we say is that the objects whose derivatives are 0, this defines what is called the kernel of a map. Okay, so this defines a kernel of a map. Okay, and the set of all objects dr omega r, okay, that defines the image of the map. Okay, so the claim is that the image of dr, okay, the image of this, that is all possible derivatives of r forms, this is a subset of the kernels of dr plus 1. That is, they're a subset of the objects r plus 1 forms, which when acted with this derivative give you a zero operation, a zero r plus 2 form. Okay. So let me just write that out explicitly and also show you pictorially what is meant by this. Okay, so take omega to be some r form. Take the derivative of omega. Okay, so all possible derivatives are basically, this is the image of the map dr. Dr being the map which takes us from, so dr is a map which takes us from r forms to r plus 1 forms. So all such terms are in the image of dr. Okay, they are the r plus 1 forms that you get as a result of performing the operation dr. And dr plus 1 acting on dr omega is 0. That is because of the fact that d square is 0. So what that means is that dr omega belongs to the kernel of dr plus 1. That is, they're in the set of r plus 1 forms such that d psi r plus 1 is 0. Okay, so the set of such size are called the kernel psi r plus 1 that satisfies this equation. Okay, this belongs to what is called the kernel of dr plus 1. And therefore, the image of dr is a subset of the kernel of dr plus 1. Okay, so to show that pictorially, so this is omega r. This is the set of all r forms. This is the 0 r form. Okay, so there's a unique r form, which is the 0 element. Okay, now when I act with dr, what this does is it takes me to the space of r plus 1 forms. Okay, and let's denote everything inside this blue circle. Okay, let's denote these as the possible results that I can get by acting dr on anything within omega r. Okay, that'll give me everything within this blue circle. Now, obviously, everything within the blue circle does not span the entire space of omega r plus 1. Okay, now within this space of omega r plus 1, there's now a map which takes me dr plus, so this map dr plus 1 takes any element of omega r plus 1 and it maps me to something in omega r plus 2. Okay, and let's denote that map as everything inside the interior of this magenta circle. Okay, so just as everything in omega r got taken to everything inside this blue circle, everything inside omega r plus 1 gets taken to the interior of this pink circle, okay, under this map dr plus 1. Now, the interesting point is that if I want to find the kernel of this map, okay, if I want to, so this blue circle is the image of dr, this pink circle is the image of dr plus 1. Now, if I want to find the kernel of this map dr plus 1, okay, I want to know which elements of omega r plus 1 are being mapped to the element 0. Okay, so the elements which are mapped to 0 include not only these objects in the blue circle, okay, because dr plus 1 acting on dr is 0, but they also include some more objects which are enclosed within this red circle. Okay, so so all of these objects, everything within the red circle, okay, everything within this red circle, okay, is mapped to a single element here. Okay, it's mapped to the single element, which is the 0 element here. Okay, so this is dr plus 1 xi r plus 1 is equal to 0. So this is all the, so everything in the red circle is all the xi r plus 1s which map to the zero object inside omega r plus 2. Okay, so everything inside the red circle is mapped to 0 in omega r plus 2. Okay, and what you can see is now that the image of dr, okay, is a subset of this red circle, which is the kernel of dr plus 1. Okay, so the image of the interior of the red circle is the kernel of dr plus 1. Okay, and so we say that such objects xi, okay, such that d xi is equal to 0. Okay, these form as a form is psi is called closed if d xi is equal to 0. Okay, so this is called a closed r plus 1 form, or if xi was an r form, you would say it's a closed r form. Okay, the interior of this blue circle, which is now shaded green, okay, this thing here. Okay, this is the image of dr. This is everything inside omega r under the operation dr got mapped here. Okay, such forms are called exact. Okay, an exact form is a form. So it's a form xi. Okay, again, which belongs to this space, but this xi can be written as d omega, where omega. So this is an r plus 1 form, which can be written as a derivative of an r form. Okay, in this case, xi is called exact. Okay, because it can be written as a derivative of an r form. Okay, so the statement is that all exact forms are closed. Okay, all exact forms are closed, but not all closed forms are exact. Okay, in other words, the kernel can be of dr plus 1 can be bigger than the image of dr. Okay, so all exact forms are closed, but not all closed forms are exact. Okay, yeah, but also if I have a closed form, okay, that is if I have a form which is whose, so let's call xi1, which is a closed form, which means d xi1 is equal to 0, and xi2 is an exact form, that is xi2 is equal to d of omega. Okay, so these are both r plus 1 forms, and omega is an r form. Okay, then the claim is that xi1 plus xi2, okay, this is also closed. Okay, that's obvious because xi1 is closed, xi2 is closed. Okay, but xi1 also happens to be exact, but xi2 is not exact. So xi1 plus xi2 will also not be exact. Sorry, not exact in general. It could be exact, we don't know. Okay, so the point is that now any form, okay, which is closed, okay, which means that you can write it as d xi is equal to 0, that xi can always be expressed as a part. Okay, it can be expressed in terms of two things. It can be expressed as xi1 plus xi2, where this xi2 can always be written as d omega, but this xi1 cannot be written as some d omega. Okay, so this part is the part which cannot be written as an exact form. Okay, so this xi is closed. Okay, but this d xi1 is still 0. Okay, and this xi2 is exact. So any closed form can be written as a part which is not exact, okay, and a part which is exact. Oops. Okay, so what you do is for every xi, okay, you map it to just the part which is you remove this sort of okay. So now what you do is, okay, so now if I take the set of all possible closed forms, I want to drop the part which is exact. Okay, and I'm interested in this part. Okay, the part which is not exact. Okay, so of course, what this means is that if I take something in here, okay, which is a closed form, but it's not exact, I can always get another closed form, which is not exact, by adding something in the blue circle, okay, to this form. Okay, so I can add this form and this form and I'll get some other form here. Okay, this form will also be closed but not exact. Okay, but what I want to do is make an identification of both of these, because these are coming, the difference between these two is an exact form. Okay, so we're interested in how many closed forms we have which are not exact. Okay, so that we define something called a quotient space, okay, which is the kernel of dr plus 1 modding out the image of dr. That is, we're only considering the part of the forms which is closed but not exact. Okay, and this quotient space, okay, that is, once I mod out the parts which are exact, okay, the quotient space that I get is called the r plus 1th de Rham cohomology group. Is this idea clear?
Yes.
Yes.
So, like that annular region, if I consider that is the one which is closed but not exact. So like between those blue and magenta, right?
No, everything inside the magenta, including the blue, is closed.
Yes, and I mean closed but not exact. I'm saying.
Yeah, sorry, right. So in the annular region is closed but not exact.
Yeah. So
Okay.
then, like, how did you define the quotient space?
Yeah. So now, if you imagine this, so let me just expand that out here. Okay. So now imagine that I take some closed form which is not exact. Okay, which is here. I can always get another closed form which is not exact by adding some exact form to this form, right? So A plus B, it gives me C. Okay. Now I can go on adding. So I can go on adding every element of this space, and I will get some kind of orbit. Okay, in the space of closed but not exact forms. Okay. Now all of these together, I just identify as a single element. Okay, I just identify as a single element, which I call the equivalence class of A. Okay, and similarly, all of these elements, which are, let's say I start with one and then I go on adding blue elements to it, that is, I go on adding exact forms, I get another set of objects. Okay, and now this blue set, okay, so let me call this D. Okay, so that so I start with some element D and I go on adding exact forms. So that's the equivalence class of D. Now, every element of the equivalence class of D is different from every element of the equivalence class of A. That's when we say that these are two different equivalence classes. So the set of such elements, okay, the set of these representatives, elements of equivalence class of A, equivalence class of D, and so on. Okay, this set together forms what is called the de Rham cohomology group. Okay, it's a group under addition. I can add two closed forms and I would get back a closed form, which is, I mean, a closed form which is not exact. Group under addition of forms. Right. So the elements of this set are defined by an equivalence class of R forms, rather than any particular R form. Is that clear? So it's like all of these elements are mapped to a single object, which we call the equivalence class, which is a representative. I mean, it's sort of like you can either think of it as choosing one of them, okay, or choosing something that represents all of them. Everything on this magenta curve. Toshif, is that clear?
Yes, sir. Like they belong to the same class, because like we are starting with some particular thing, and then we are like by addition with things inside the blue. Like we
Yeah.
are on circle. So
Yeah. So basically all elements on this pink are in the equivalence class of xi1.
yeah, but just like we like, how will we know like what xi1 to start with? Like, so this xi1 is not special.
Okay. So now the point is that what you okay. So it doesn't matter. You start with any xi1. Okay, you start with any xi1, and using that you can. So if I started with any other xi1, I would have still got the same circle,
Mm.
right?
Okay.
Because they're all related by adding some exact form.
Yeah. Then if I call that some xi2, then xi1 and xi2 belong to the same class.
Right, xi1 and xi2 will belong to the same
Yeah.
class. So in that case, xi1 and xi2, you'll say that or you say that they are equal. I mean, they're related to each other because they belong in the same equivalence class.
Okay.
Okay, yeah, and it turns out that there's basically an addition operation on these equivalence classes. So if you add two objects in one equivalence class, right, this will give you xi1 plus xi2 plus d omega plus d omega prime, and this belongs to the equivalence class of xi1 plus xi2, right? So this group is this forms a group really under this operation of addition of differential forms. Even though you're using representatives rather than the original differential forms, okay, uh, this is basically now going to form a group, okay, under addition. And this group is called the Dirac cohomology group. Okay, so the set of elements, a group is defined by what are the elements of the group. The elements of the group are these operations, sorry, these equivalence classes. Okay, each equivalence class is one element of the group, and the operation is addition of these representatives of the equivalence classes. Okay, to get another member of the group. Okay. Okay, so let me define one last operation. So this is an interior product and a relationship between this interior product and what are called d derivatives of these forms. So the interior product is very simple. So given a vector field x, okay, we define the interior product Ix, which takes an R form to an R minus one form. Okay, so the exterior derivative took us from an R form to an R plus one form. Now we can go from an R form to an R minus one form, but this requires us to supply one interior derivative x. It's defined such that Ix omega acting on so x1 through xr minus one. Since this is this, so if I start with an R form omega, I now claim that I have an R minus one form, and the action on these R minus one objects is just omega acting on x through x1 through xr minus one. Okay, so it's very simple to understand what this operation is. We just fed it one extra x. Okay, and this tells us how it acts on these remaining objects x1 through xr minus one. Okay, so we can see in coordinates what this means. So x is equal to x mu partial x mu. Okay, and omega is 1 by r factorial, omega mu1 through mu r, dx mu1, wedge dot dot dot, wedge dx mu r. So the interior product, Ix omega, is now defined as 1 over r factorial, summation s is equal to 1 to r, minus 1 raised to s minus 1, x mu s, omega mu1 through mu s, through mu r. So I replace one of these indices by this x mu s index. Okay, dx mu1 wedge dot 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 wedge dx mu r, but I omit the mu s index over here. Okay, how did I get this? So I just acted with omega acting on x1 dot 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 xr minus 1, but I didn't actually act on the x1 through xr minus 1s. Okay, so I omit all the x1 through xr minus 1, so I don't act on those. Okay, and then you would find that you get something like this. Okay, that is omega. I'm only considering the action on x. Okay, and this x can be acted on by any of these indices. It can be acted by this mu1 index. It can be acted on the mu2 index, by the mu-r index. So in general, I'm denoting it as a summation by the mu-s index acting on the x. What it does is it picks out the x mu-s coefficient. Okay, and it drops this dx mu-s hat. Okay, but depending on where this mu-s hat appears, okay, I'll get a minus 1 raised to s minus 1 sign as the overall coefficient. Okay, and here what I get is omega 1 mu 1 dot 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 mu s mu r. Okay, so it's a contraction of this index with this index. Okay, and now another way to rewrite this, okay, is instead of putting this contraction on the mu-s index, this mu-s index is arbitrary, so I can write that as an index nu. Okay, but this index nu could have appeared in any one of these places, but it doesn't matter which place it appears. This is fully anti-symmetric because of this minus 1 raised to s minus 1. So I can just push it always to the first place. Okay, and since there are r terms over here, I will get a factor of r, which will cancel with the denominator. So I get a 1 over r minus 1 factorial. X nu omega nu mu2 to mu r dx mu2 to wedge dx mu r. Okay, so now there's no ambiguity about which thing I'm dropping. I just have only indices mu2 through mu r. Okay, so and this is an object that is an r minus 1 form. Okay, so if we do an example in R3, okay, with XYZ coordinates, if you take X to be equal to EX, okay, that is just the basis element along the X direction, partial X, and we take dx wedge dy, and let's take the interior product of that with EX. So it's dx tensor dy minus dy tensor dx acting on EX, and I leave a slot open, okay, for acting on another vector. And so this dx acts on EX and this dy acts on EX, okay? The action of dx on EX is giving me 1, so that gives me just dy. And this dy tensor dx, dy when it acts on EX just gives me 0, okay? So this gives me 0, so I get just dy. And similarly, IEX acting on dy wedge dz will just give me 0. IEX acting on dz wedge dx will give me minus dz. Okay, any questions about this interior product here?
Sir, I didn't get that thing of keeping one slot empty. Huh?
Oh, the one slot empty is basically this, right? I mean, what is this, right? This is an anti-symmetric product, but I mean, you can write it as a tensor product where I've anti-symmetrized over the indices, right? So I can think of it like this, and then I can think about the coefficient as, let me anti-symmetrize the coefficient. Okay, and now when I act on x mu, okay, I'm acting on x mu. So let me say I'm acting on x mu in the first slot. So the way to think about it is this index is being eaten by the mu1 index. Okay, and this is setting nu to be equal to mu1. Okay, and omega mu1 through mu r. Okay, this is one way to think about it. Another way to think about it is, supposing I had written the original wedge product as is, then I would have, I would imagine terms like this, but I imagine that I also have I also have every other permutation of these indices, right? So every other permutation comes with a minus 1 sign raised to the, the sign of that permutation. And I would have terms like this, for example, dx mu1. And now this dx mu2, when it acts on this, okay, is going to replace the nu by mu2. Okay, and then the mu3 would replace this nu by a mu4 and so on. But that would get rid of this dual vector and it would get rid of this vector, right? So I've got rid of the dual vector. I got rid of the vector basis, and I only have the coefficient, and I've set it equal to the mu s coefficient. Does it make sense why these terms are dropped?
Yes, sir, like delta function mu.
Yeah, and basically the point is that since it's fully anti-symmetrized, you don't know which of these mu's is appearing in the first slot, right? Which is acting on the x, right? I mean, all possibilities are allowed. Okay. Okay. Yeah. And so now, well, basically, once you define this interior derivative, there's a nice relationship between the Lie derivative of forms, okay, and this interior product. Okay. What you can show is that the Lie derivative of omega. Okay. So this Lie derivative with respect to x of omega, where omega is an R form. So Lie derivative of an R form is also an R form. This is equal to the derivative acting on the interior product of omega plus interior product acting on the derivative of omega. So this is an R plus 1 form. When I act with the interior derivative, it becomes an R form. Sorry, with the interior product, it becomes an R form. And now this is an R plus 1 form. Sorry, this is an R minus 1 form. When I act with the interior product on omega, it reduces the rank of the tensor to an R minus 1 form. And then when I act with the derivative, it becomes an R form. So these are two different R forms. I have to add those two R forms, and that gives me the Lie derivative of omega. Okay, I won't go through the proof. Okay, that the proof is there in Nakahara. Okay, I encourage you to look at it. There's a simple check for one forms. At least do the check for one forms. Okay. And now you can show some more interesting identities. These are also given in Nakahara. So the interior product of the Lie bracket of xy acting on omega is the Lie derivative of x acting on iy omega minus the Lie derivative of y acting on ix omega. I think there's a typo in Nakahara where this instead of Lie derivative of x, they just have x acting on iy omega, but that doesn't make any sense. And then Ix acting on omega wedge eta is equal to Ix omega wedge eta plus minus 1 raised to R omega wedge Ix eta, where omega is an R form. And also Ix square is 0. Okay, that's easy to see, right? If I feed in two x's to omega, right, this should just be 0 because it's fully antisymmetric. Okay, and then you can also show that Lx Ix omega is equal to Ix Lx omega. Okay, so I mean, these are some useful properties. We probably won't discuss much about this interior product in GR, but the exterior product might be useful. And also this Dirac cohomology group I mentioned is useful. Also, another place that all of this is useful is you can entirely reformulate Hamiltonian mechanics. Okay, so everything that you learned about Hamiltonians and flows in phase space, okay, in a classical mechanics course or dynamical systems course, everything can be reformulated in terms of differential forms. So if I have a complicated phase space with xi, pi as different coordinate variables, and so this entire space is described by coordinates qi's and pi's. Okay, this describes a set of coordinates. Okay, so this is in configuration space. So the configuration space is a manifold. Okay, the phase space is a manifold. Okay, and what you can argue is that okay, you can argue a couple of things. Okay, one is you define a form like this. Okay, dq wedge dp. Okay, so you define what is called a symplectic 2 form. Okay, and I forget the exact details. Something like this. Okay, I forget the details. You can look it up in Nakahara, but basically you can talk about the Hamiltonian flow. Okay, the flow generated by Hamiltonian of any observable. Okay, you can talk about that Hamiltonian flow in terms of like some kind of diffeomorphism on the phase space. Okay, which is generated by some vector field which is related to this Hamiltonian. I forget how the symplectic forms come into the story. Anyway, I mean that's another lecture by itself. So, but I just want to motivate that you can reformulate all of classical mechanics in this language, and it makes it much more intuitive once you understand these geometric concepts. Okay, and de Rham cohomology is useful. Well, magnetic monopoles is one place, but even understanding things like a simple pendulum, when you can make full oscillations, okay, not just small oscillations, but understanding that okay is I mean understanding the concept of de Rham cohomology is useful there. Okay, let's stop here. Stop the recording.